Good afternoon, everyone. Welcome to today's sustainability seminar. As most of you know, the focus of the talks this semester have been on water quality, use, and conservation, and we continue that theme today. We're very pleased to have with us as our speaker John Bauer. He's president of Wahaso Water Harvesting Solutions up in Chicago area. John is a Duke University alumnus with an MBA from the University of St. Thomas. He's also a senior faculty professor at the Keller Graduate School. His company, Wahaso, is a design-built firm specializing in custom commercial systems for harvesting rainwater, greywater, and other on-site water sources for non-potable reuse. Wahaso provides consulting and system design services to engineers, architects, and then delivers systems that are pre-assembled and tested on skids for installation at local contractors. The Chicago-based company was founded in 2008 with a team of industrial professionals and has designed systems for well over 200 projects in the U.S. and Canada. So today's seminar is entitled Water Harvesting in Commercial Properties, and John's going to discuss this growing interest in on-site water reuse systems. So, John?
Great. Everybody hear me all right? Well, lovely weather you have down here. I should come down more often. You know, up in Chicago it's still kind of chilly, but here it's like a spring day, so very, very pleased to be down here. Well, thank you so much for having me down, for having Wahaso down. We're very pleased to spend time with you and to share kind of what we're up to right now. And this is really meant to be kind of an overview of water harvesting in general. So we're going to talk about terms and trends. We're going to talk about the whole process for designing a system from scoping all the way through to delivery. We'll talk about some of the components we use as well, and then show you how that comes together in a number of case studies depending upon the amount of time we have. There will be time for questions. This is not meant to be a really deep technical discussion, but if you want to get technical, I can, even though I'm not the engineer. I've learned an awful lot about water harvesting in all of our systems in the last 4 years, so I'm a near expert here, so I can certainly answer most of your questions if we get there. But the idea is a learning process is that by the end of the session you would be able to really understand what the key trends and drivers are that are growing the water harvesting industry, and it is growing very rapidly right now. Explain the process for designing a system and the importance of the scoping stage, the first stage as you'll see. Define the water harvesting sources and identify the practical uses of treated non-potable water. List the major components of a commercial harvesting system and their purpose, and then be able to use examples that would show how the whole process works together. Sound like a good plan? All right, well, just Nancy talked about us briefly already. I'm not going to spend a whole lot of time just to say that we are a pretty new company in a new industry, and our strategy was to bring together a senior executive team with a lot of broad knowledge in engineering of fluids and systems like that, as well as electrical engineering. So that's really helped us progress very quickly and become an expert in this industry, even though the industry itself is quite new. The idea of commercially producing non-potable water on site for harvest in a commercial system or commercial building is relatively new. But we're seeing a lot of systems now going in across the country. And as Nancy mentioned, we've done probably as many as 200 systems we've worked on so far. So we're getting a lot of experience out there. And our approach was a turnkey basis from design all the way through to the installation, which allows us to control that whole process and make sure the system that we're designing is going to work like it should at the other end. You can't see all this. It was just really meant to show you the kind of variety of projects we've done for commercial buildings, for housing, properties. The military now is very aggressively pursuing water reuse, and we're doing a number of projects across the country. A lot of government projects. It really comes down to who's got the money, who's willing to invest in these systems when the ROI may not be great with current water prices. So military, government, City of Chicago, being a green city, is also very interested. Mayor Daley left a legacy of a number of green initiatives, several of which were these systems installed. So we talk about water harvesting. You've heard of rainwater harvesting. We broaden the definition a little bit. We say that water harvesting is the collection, cleaning, storage, and reuse of multiple on-site water sources, which we'll talk about in a minute, with the idea we're trying to reduce the consumption of municipal potable water. So it's all about how do we avoid using high-quality drinking water for non-potable purposes like flushing toilets and irrigating landscaping, and when that same water source could be replaced by non-potable water sources. There are some confusion about these trends. The terms are, we see in the industry are vary a bit, so we're seeing them kind of settle into these definitions. When we talk about rainwater harvesting, we're talking about harvesting water that's come from a relatively clean surface above ground. Most commonly a rooftop, but sometimes we'll see other solar shades and those kinds of things that are used for rainwater collection. Very clean source, very good source, requires a minimum treatment on our part, so rainwater harvesting is very popular. But there are other viable sources in trying to maximize our water reuse, one of which is stormwater. So that same rainwater, once it's now been contaminated on the ground by oils and salts and fertilizers, that kind of thing, can also successfully be captured and treated and used for non-potable purposes. The term greywater is spelled 4 ways, G-R-E-Y, G-R-A-Y, 2 words, 1 word. It's all the same thing. But in that case, we're talking about what is normally municipal water that's been used once already, generally for showers and sinks, sometimes light commercial uses. The idea is that it's not so heavily loaded that we cannot safely and easily clean that on site and reuse that as a viable source of water. So we'll talk about greywater harvesting again a little bit later on. Groundwater is a good source, too. Here in the Illinois area, we have a lot of groundwater, particularly where we have basements and garages. We're able to take water out of ejector pits and use that. And unless the soil is contaminated, that's a great source of water for reuse. The term reclaimed water has been reserved by municipalities that are taking sewage, treating it to a level that's safe, and then sending that back into the community for reuse. So we don't do have any reclaimed water in Illinois, but it's very popular down in Florida, down in West Coast, California, Arizona, Texas are all now providing reclaimed water as a water source. And any one of these sources, once we have processed that water, once we've usually filtered it, we've sanitized it in some form, we've stabilized it, then its definition changes to a common term that the industry is calling on-site treated non-potable water. So we've raised all those water sources to a standard that is now safe for application in non-potable purposes. And that's important to note because regulations may say that it's illegal to use gray water for flushing toilets, for example, but we're not flushing toilets with gray water. We're actually flushing toilets with treated gray water that's now on-site treated non-potable water. So when we want to make sure as the water quality changes that the definition is changing with it. Let's talk about the trends, what's going on out there. First of all, there is a water crisis on the horizon. You folks, with your sensitivity to sustainability, are probably more aware of that than the regular U.S. citizen, for example. But there are water shortages already on the horizon throughout the world. And even in the U.S., where we think we have a lot of abundant resources, water is an issue and will continue to be in the future. So it's said that water will be to this century what oil was to the last century. Started out the century being very inexpensive, abundant, no one thought about using it, and by the end of the century it will be scarce, very expensive, and a political political issue. So that is a problem we see, and as you look to the future, you say by the year 2050, you think about changes in global warming and the population growth. It looks like about half the counties in the U.S. would be, we consider it extreme or very high risk areas for water availability, for municipal water supplies. So even in areas like Illinois, where we have a lot of rainfall, we have the Great Lake right there, we're foreseeing issues there too. The amount of water that Illinois can take out of Lake Michigan, for example, that maximum billions of gallons of water a year is regularly reached every year already by the current demand. So there's not an additional room for more growth of water out of Lake Michigan. And then all the communities around the Great Lakes that are using primarily aquifers, deep and shallow aquifers, are seeing the aquifer levels drop year by year because we're taking it out at such a rapid pace that it's not being replaced like it should be. So there may not be a critical issue now, but as water managers look to the future, 5, 10, 15, 20 years, they're seeing that there are issues. And that means that we want to find ways to slow the growth of municipal water usage. That's what the main reason for using water harvesting is to slow the growth. So it's not the only solution, it's one of the toolboxes that we see municipalities using. So we have several mega trends that are driving this water harvesting industry. I messed up. There we go. First, we start with that predictable shortage of potable water and the concern about conserving water. So that's a big mega driver right now. We also see the green movement, this whole concern about the environment and the general concern about sustainability practice in general as it applies to water and electrical and others, and certainly all of you are very well aware of that. The general concern for the environment, that's a driver. So we see a lot of projects driven by LEED certification where They want to achieve greenness for the building. They want to make, certify the building as green. They're looking for ways to do that, and water being one of those. And we'll talk more about LEED in just a minute. So the green environment's a driver for us. And the last one is this whole area of stormwater best management practices, where communities are realizing that the huge rooftops and parking lots and roads that are throwing off mass amounts of contaminated waters into our waterways, or in the case of Chicago, being put in with the raw sewage that has to go to the treatment facilities around Chicago, and it's all mixed together right now, as you know. And so in a big rain event, what happens is that the treatment plant simply cannot handle the vast amount of water coming in a big rain event, and they have this mix now. They have this mixture of sewage and stormwater. What do they do with it? They just discharge it raw. I mean, there's no other choice. And so that's a bad thing. So what we see is communities like Chicago, New York, California, and L.A. requiring property owners to capture that stormwater, to treat it, to store it, oftentimes at hundreds of thousands of dollars per property, basically to take all that water, filter it, put it below grade, and then over the next several days when the storm event is over, to release that water more slowly back to the municipal sewage treatment area, which is just fine. That helps solve the problem of overwhelming the municipality. It helps to do pre-treatment to keep that water from just running into the watershed. But a property owner gets zero value out of that water. They spent $500,000 to detain 250, 300,000 gallons of stormwater in an event, and then they're releasing it back, so they get no value out of it. So the logical question is, couldn't they tap into that detained stormwater and use that for flushing toilets or irrigating the landscape? And the answer is, of course we can. And in a system like that, it may be as little as 5% incremental cost to be able to adjust that system so we can retain that water for reuse and harvest that. So that's a great opportunity for us, and that's another driver of water harvesting in general. So you have those three mega trends. We also have the incentives that are out there. We do see some grants now. Illinois has the Green Infrastructure Grant that's providing dollars that can help to pay for these systems. There are other incentives we're seeing too, although it's early for the incentive side. More commonly, we're seeing the sticks out there, the stormwater management requirement that Chicago and other cities have. We see states like California that are prohibiting the use of municipal drinking water for irrigation, for example. So it leaves property owners in a question of how they're going to irrigate their landscaping if they have very little rainfall and they're not allowed to use municipal water for that. Tucson passed a law 2 years ago that requires all new commercial and residential buildings to be plumbed for gray water, to have the ability to separate black water from gray water and be able to send a separate non-potable water stream to the toilets. So that's looking to the future and realizing that a building that's built today is going to still be in service 20 years from now, and they got to get the plumbing right at that point in time. So all these trends and influencers are driving the industry and really creating an opportunity for water harvesting. This is some research that was done in the industry back about 2 years ago, but the results just came out recently showing how many of these systems are out there, where they are as well. And we see there were about 20,000 systems total that were installed across the U.S. In the year 2009, across residential, commercial, and government, above ground, below ground. And if you add up the dollar value of those back then, it was about $500 million in sales for the industry. So our guess is that in the last 2 years, the industry's grown probably 30 or 40%. So we're looking now at probably nearly $1 billion in economic value for these systems. Where are they? Well, they're where you would think they would be. They are in the dry states primarily, down in Texas, California, New Mexico, Arizona. But we see states like Illinois, Georgia, and other states where the water crisis is not so bad, also being leaders in these systems. So we see them growing and continue to grow in the next several years here as the whole category grows. What's in it for owners? Why would owners put a water harvesting system in? Well, first of all, there is that savings on municipal water and sewer and water charges, and that varies greatly by the municipality where you're located. We did one system in Chicago that saved 3.5 million gallons of water a year, and at that time it was saving about $10,000 per year in water and sewer charges. A very similar system in New York saved the same amount of water, and the savings was $35,000 a year. So where you are has a lot to do with what that ROI is. Now, Mayor Daley just recently announced he's going to double the water rates that Chicago is charging over the next 5 years. So that means we used to have an ROI of 15 years on a system will now be 7.5 years. So that'll work to our advantage. But that's not the only reason that property owners do the systems. They're also looking for ways, like we talked about, to turn a liability, which is stormwater management, into an asset, the ability to save water and to help the resources. They see it as a way to protect the environment, to be green, to really show that they are stewards of our environmental resources, and that's often a driving influence in systems we see. The need to follow regulatory requirements or to achieve incentives. LEED says, the USGBC said that a LEED certified building, for instance, will have a resale value that's worth about 15% on the market versus a non-LEED certified building, and that's due to the fact that those buildings have lower operating costs, but also because green's in. People want to be green, and so those buildings have more value. So we'd say that even though a system may not have paid back yet through water charging savings, that building may be worth 10-15% more in the market. And finally, being green is good PR. I mean, having a water harvesting system and for your employees, for your customers, for the community says, this building owner cares. We care about the environment, and we're doing our part to conserve our resources. How many of you are LEED certified? Anybody? One? Okay, well, then I'd say that LEED, as you know, is the way of certifying a building being green, and there are different levels of LEED, certified, silver, gold, and platinum, and it's all about getting points and earning points for different elements of the initiatives. And if you really want to get to those higher levels of gold or platinum in LEED, you've really got to do water. You have to do water conservation, in addition to energy and materials and site and all the other things that LEED certifies as being green. But there are 4 categories that would influence points through water savings. There's water use reduction, innovative wastewater technologies, for instance, Greywater harvesting or stormwater reuse, stormwater design, water efficient landscaping. So one of the things that we do, and we work on a number of LEED projects, probably maybe 25 or 30% of the projects we do are in some kind of a LEED certification effort, and so we're happy to help out and do the calculations that help the property owner try to determine how many points they can earn from a particular system. And we've done systems that can actually fire on all 4 cylinders. We're able to do a multi-source, multi-use system which can earn points in all 4 categories. As we look at commercial properties, think about where it makes the most sense to do water harvesting. I mean, homeowners are in the lead of this. They are the homeowners with rain barrels and showing that they want to reduce their water footprint are great proponents of water harvesting. But if you really want to make a big difference, you got to go to the commercial buildings. And why is that? Well, because commercial buildings tend to be heavy consumers of water, and they also tend to have big surface areas that can throw a lot of water off. So a typical office building with 250 employees could use 500,000 gallons of water a year just for toilet flushing. The big evaporative cooling system on the roof could use 500,000 to 3 million gallons of water a year. All that fancy landscaping requiring another 3/4 of a million gallons of water a year. And at the same time, they've got big rooftops that are throwing off 500,000 gallons of water a year. Cooling coil condensate, another 500,000 gallons of water a year. The parking lot, another 2 million gallons of water a year. So you see, one building could easily save 2 to 4 million gallons of water by replacing that potable water with the non-potable water already available on site. And if you look at different types of buildings like shopping centers and offices, and look to see what the major components of their water usage is, we see that at least for these first 3, where there's not a whole lot of potable usage, that toilets and urinals, cooling towers, and irrigation can make up 90% or more of the total water consumed by that building. And if the water consumption is 2 or 3 million gallons of water for a particular building like that, we can see that the potential is very significant in making a major reduction in the total municipal water consumption of that building. We did this Harold Washington Social Security building downtown Chicago. It was an existing building and a retrofit. We saved 3.5 million gallons of water a year. My partner said, "Gosh, that's one building. Can you imagine if we could do 400 buildings in Chicago, and what the kind of impact we really could make? We'd be talking about hundreds of millions of gallons of water saved per year through these systems." And he was right. But water harvesting is a new industry with new challenges. I mean, we, as kind of one of the leaders in this area and an early participant, are saying that there is a lack of public education understanding about how the systems work, what's legal, what's not legal, what the potential is to save, how that would be done. There are many regulatory barriers that are out there, mostly because the regulations we have in place now in Illinois, Chicago, and the rest of the country are really outdated, and they're going back to earlier days when there was concern about public safety in these systems and worried about that. And so in Illinois right now, it's illegal to flush your toilets with rainwater. You can't do that legally. Doesn't mean we can't get an exception to that law and pass that law, but the health department is, and it really comes down to the public safety concern, and that is that if you did take raw gray water, for example, and let it sit around for 3 or 4 days, then started spraying the landscaping with it, that would be a health issue, right? It would be a health hazard due to that, because you'd have all the bacteria in that water untreated that could create a health hazard. And similarly, even in a toilet flushing, if the water wasn't treated and that water's in the tank, the water's being sprayed as you flush, there's a concern about public health there. And so that's the first concern that the regulations are there for, is to protect public health. The other question that we see is the whole issue of a backflow situation, where if a non-potable system was connected to a potable system and we had a backflow situation, a broken water line that created a vacuum back, you could pull that contaminated or non-potable water in and contaminate the public safety, the public water supply. And so that's why those are there. And so to get past those barriers today with the law still in place, we generally have to go before a standards and tests committee to be able to demonstrate that our system will meet those concerns about public safety. There are emerging industry standards. There are inconsistencies out there. I talked about the terms out there and the misnomers and how they're sometimes played out. The question of how clean is clean, what is safe when we talk about non-potable water versus potable. I mean, there are really good standards for public potable water, but the standards for non-potable water, flushing a toilet, or non-potable water, watering landscaping, for example, those really aren't set yet, and every community is trying to establish what those standards should be. And so we have to deal with that community by community as we have interest in these systems and are trying to get them past the local regulatory environment. I talked a little bit about the undervalued cost of municipal water. I mean, I talk about it being like us out there trying to sell a hybrid car when gasoline was 25 cents a gallon, and it costs you $10,000 more for the car, and you'll save, 8 cents a gallon in fuel. And it's just like, you can't get there from here. And that's still true. It's changing a bit as we see municipalities realizing that their water supply is undervalued, and it's an opportunity to raise revenue like Chicago is. We'll see the water rates go up, and that will help us in the same way that higher fuel prices have helped alternative cars like the hybrid cars. Emerging technologies and learning. You'll see when we show you our systems that these are really pretty much standard types of filters and pumps and things being used in a unique new way. And in a unique way we're processing gray water, rainwater, etc. So we are learning, as these systems have been installed now, what kind of components hold up, what the best standard is, how to re-engineer them, make them more efficient, lower cost. So that's all part of any new industry, and certainly is true in ours as well. And we're basically working with all these to try to grow the industry in a very profitable way long term. The other thing that kind of haunts us is this Greywater conundrum, this idea that we have a building that's being designed in the year 2012. It may get built by the year 2014, and that in 2055 that building will still be here, right? It'll still be in place and still being operating. Well, there's only one time in that building's life when we can practically go in and plumb that building separately, separate the gray water from the black water, and separate the potable water from the toilet supply. And that's when the building's being built. So a building where once those walls are up, we cannot, economically go back in and replumb the building for gray water or for non-potable water in the toilet. So there's only one time to do that. So that's what we're getting out there now. We're saying, to architects and engineers, have this discussion before the design's done, before the walls go up, so that if they do in fact want to do that sometime in the life of the building, they make the decision now and not later on. And that also makes it more challenging for us as well in retrofits, where we have an interest in collecting gray water and there's no way to get to it practically, and then also in using non-potable water to flush toilets, we really can't in an existing building. So that's a challenge for us. It doesn't mean there are good retrofit opportunities. We can talk about those. For instance, rooftop rainwater for irrigation is a great retrofit opportunity, or rooftop water for cooling tower makeup is another good way that we can very economically go in and retrofit that for a new building, or an old building, I should say. Let's talk about the development process, what we go through for developing a system and the different steps that are there. And you'll see that there are 5 major steps, starting with scoping, where we're thinking about how a system we design, to the actual technical engineering of the system, the fabrication of it, installation and testing, and then training, service, and maintenance. And we like to get involved at the very beginning of the project when we have a building owner, an architect that are interested in sustainability, where the building owner has expressed an interest in these systems, and get involved at that stage to help them scope it and think about what the system might look like. And we'll talk more about scoping in a minute, but the output of that, in addition to having a concept for the system as an output to that step, we also have a rough budget number so that the architect can say this system would save this much water per year and it would have this kind of a general cost. We can get them at a rough number. And if the building owner says, yes, I want to put that in the budget, let's move forward with the system, then we work with our engineers and generally the engineers of the building to finish the design, to do the fine engineering of it, and then to provide the drawings and the specifications so that that system is now part of the building specifications. It's now part of what goes out for bid. And then at some point, the whole building goes out for bid. And in addition to the plumbing and the roofs and the windows and everything else, this system now becomes part of the plumbing specs for the building. And we get calls then from the plumbing contractors or the mechanical contractors who will do the plumbing for the building. And this system being part of that, often a black box in their perspective, they will come to us and we will then partner with them to have the system built, to fabricate it, and get it installed, make sure it's working right, and like it was designed to do. And then once the building is commissioned, and that could be, sometimes 2 to 3 years from the time we started here, the building is now actually built, the system's installed. We'll come back in then and work with the building staff to show them how to operate the system, how to maintain it, and how to understand what kind of faults and problems there might be and resolve those locally. So let's talk now about a couple of these steps in depth, starting with scoping and then talking about the system design and fabrication as well. Any questions before I go on? All right. Well, let's talk about scoping. Scoping is a critical first step in any system design, and this is our opportunity to really evaluate and estimate potential supplies and demand. And you'll see that there are multiple supplies for multiple uses, and our objective is to try to optimize them so we're really maximizing the savings of the system overall. At this stage also, we draft a system concept. It's usually in a Word document. It just basically says, here's how this thing would work. We'll capture water here into this kind of a cistern, this kind of filtration, this kind of sanitation, this kind of pumping, so that you have an explanation of the system and maybe a rough schematic which can really provide a discussion point for the engineers, the architects, and building owners to say, is this what we want to do? Does this make sense for this building or not? We also at that point can determine roughly the amount of storage we'll do. How that storage, it's a big component, is how much water we're storing and where we're storing it and how we're storing it. So we will come up with a recommended amount of storage. And then also the system mechanical requirements. How much space will this thing take? How much mechanical room do I need? Where am I going to dig a hole for the cistern, for example? That's part of this discussion as well. And then from the architect's standpoint, maybe most importantly is, what are we talking about here? Is this $50,000 or $500,000? And what's the installation cost going to be? So out of scoping as well will provide that rough budget estimate so they really have the tools they need to be able to make a decision about going forward with the system in general. First step is evaluating water sources and applications, and we talked about some of these already. Rooftop rainwater, surface stormwater, greywater. There are other sources as well. Cooling condensate is a great source of water. A big office building with a lot of floors can easily throw off, with their multiple blowers, 8, 10, 12 gallons a minute of condensate when all the system's running, and that equates to literally millions of gallons of water a year. Most buildings, that water just goes into the sewer system or storm system. It's lost, and yet it's a very clean, viable source for reuse. So it's often forgotten. People think about rainwater and forget they've got tens of thousands of gallons a month coming from the cooling system. So we'll apply that. Steam condensate, we did a project in New York. We're harvesting all the condensate from the steam heating system, groundwater ejectors, cooling tower blowdown, processed wastewater. Those are all potentially viable sources for reuse on site. And then this other side of this, you want to say, well, what kind of uses do we have? How can we maximize use of it? So we'll often look at projects where the engineer is interested in taking rooftop rainwater for landscape irrigation. That's great. That's fine. But here in Illinois, we only have 4, 5, 6 months out of the year where we're doing any kind of landscape irrigation. So the rest of the year, that system's sitting idle. So we'll say, okay, that's great. Can we also look at toilet flushing? Well, why not? Let's see if we can flush toilets year-round and replace all that toilet flushing water with non-potable water. Cooling tower makeup, those guys use millions of gallons of water a year, and generally when we do a cooling tower makeup system, it'll suck up, every drop of rainwater we've got will go into that cooling system, and condensate as well. They're big, big consumers of water. And many of the projects we do will do 2 or 3 sources for 2 or 3 uses, and then we really start getting into a system that's making a big impact and can really save millions of gallons of water annually. So we look at month-to-month flows. A lot of those supplies and demand are seasonal. Think about rainwater, think about irrigation or cooling tower or boiler makeup. Those are highly seasonal sources and uses of water. So what we do is do a chart like this, which helps us identify how closely we're matching supply and demand to non-potable water, and look for areas where there are opportunities either to find more supply or to find more demand, so we can use excess and really try to balance that. So this is a great stage. It's still all on paper right now. There's no other cost here, and we want to make sure we've optimized the system during that stage. I said before that the storage of the water, how much we're storing, is a really critical issue, because the cost of storing water, of creating a cistern, ranges anywhere on the low end from probably $1, $30, $40 per gallon, up to $3 or $4 per gallon or more. Well, we're talking about whether we should have a 20,000 gallon cistern or a 30,000 gallon cistern. That's a 10,000 gallon swing. We're talking about a $25,000, $30,000, $40,000 swing in the cost of that system. So we originally started kind of just eyeballing the amount of storage we would need and recommending a rough number, and we realized that we needed better data than that. And so what we do now is we model different cistern size. We get down to demand day by day throughout the year, and how much demand are we going to have for toilet flushing, irrigation, etc. And then we go back in time and we look at the supply, particularly with rainwater, and we look at that location for the last 6 years and look at day by day how much rainfall they had. And then we model what would have happened with different cistern sizes at each year based on different cistern sizes we had. So what this shows you is that in this particular case, that as we add more storage capacity, the amount of savings in water we have versus total demand is going up, up, up. And at about 30,000 gallons of storage, where we're saving about 92% of the water, that's how efficient we are in meeting the demand with our water sources. We're at the point where adding a lot more storage doesn't buy us a lot. So you go from 30,000 gallons to 40, and we're only saving 13,000 gallons of water a year. Probably not a good investment. So it just gives us a good data to be able to demonstrate what size cistern we should have and make a firm recommendation based on data. So that's what happens in scoping. Remember, the output's going to be a rough budget number and a concept. Then we want to get into the actual system design. And when we are designing a system, our first objective is we want to make a significant and meaningful impact on reducing the amount of municipal water out there. We have gotten calls from lead project managers who are saying, hey, we're trying to get to LEED Platinum. We need 2 more points. What's the least system I've got to do to get 2 points? And my lead guy's going, yeah, I know that. I've been in that discussion before. That happens, and we cringe at that, because we're saying, boy, you could just 10,000 gallons more storage, you could save twice the water you're saving. No, they want the least cost system. So we do get in those situations, and generally we can come back and influence that and really try to, without a lot more cost, make the system a lot more efficient. We want to match a system to meet the unique characteristics of each building. Think about that, whether it's a residential building, an office building, whether it's located with a big roof or small roof, an area with a lot of rainfall, seasonal rainfall, no rainfall. Every building is different. Every building design needs to be a little bit different as well to try to optimize that system. And so every system we build really is custom fitted to a particular project. From a public health standpoint, we want to make sure the water is safe for storage, that it's not going to go anaerobic on us, the water is going to be stable, that it's going to be safe for application, not do any harm out there. We want to keep the system as simple as possible. And we can make the system complicated, but when that happens, we find that the first sign of trouble, they'll bypass it. And so you got this very expensive $150,000 system, and they've got this valve they've thrown, and so it's sitting there idle. We don't want to see that happen. So we do our best to try to keep it as simple so that we're not going to have that problem, and then at the same time keep the cost per gallon as low as possible too. So we're really we're getting a big impact without a lot of cost per gallon overall. When we design a system, there are 4 major component areas that we're evaluating. First is that we have to have some method of capturing water and doing some preliminary filtration of that water and storage of it. So that first step, the pre-filtration, the storage is one of the biggest first steps. And then we have the second, processing the water, some kind of filtration, sanitation of the water to make sure it's safe. Now we're sitting with a big amount of safe water, but it's not pressurized. We've lost municipal water pressure, so we have to add pressure. And that can be from as simple as a little 10-gallon-a-minute submersible pump up to a very sophisticated triplex pump system for a multi-story building. Very expensive, but very sophisticated. So we're matching the pressurization requirements to the building and the needs. And then all that's being monitored and controlled by a central processing unit system that's going to manage all the operations of the system and be able to report on the system conditions and whether or not there are any issues with it. So what I'll do now is kind of take you through each of these and show you kind of what the tools we have in our toolbox, and you'll see how those are applied later in the case studies. First of all, primary filtration storage. This is where we want to capture the water initially, try to keep any kind of contaminants as much as we can out of our storage cistern. And there are two primary methods. One would be a natural methodology using vegetated swales. And we certainly would encourage this as a way. Think about these swales along roadways or in parking lots, and the water drains into the swale, and you've got a couple of things happening. You've got the plants, which are digesting some of the carbons and nitrates and other kinds of contaminants that are in there. The soil level carries microbes that are also digesting some of those contaminants, and this is getting pretty sophisticated now. There are companies that do engineered soils specifically for bioswales, where they have known contaminants that are coming off a water capture area or a watershed and are modifying the soil to maximize its ability to filtrate that water and clean it. In this case, down below the soil layer, there's a sand layer, and below that, all along here, we have a storage cistern, which is capturing the water. So the water, by the time it's filtered through the soil, the plants, the soil, down to the cistern below, is really in a very high level of condition and ready to be used for reuse. More typically, though, we're doing some kind of mechanical separation. This is Jim Sharp, our operations manager. He's showing a vortex pre-filter. This would replace a typical first flush system and make this system a lot less maintenance. The water comes in at an angle, a side angle like this, and spins in a vortex into this filter basket, and the vortex spins it through the filter membrane here, where it goes off to our cistern here, the clean water, and then down to the hole in the bottom. We have sticks and gravel and other kinds of sediment will drop directly out, and those will go to the storm system. So this is kind of a self-flushing pre-filter. They're great for relatively small rooftops up to anywhere from 20 to 30,000 square feet. But we also do projects where we're talking about 500,000 square feet of rooftop, and we still need to do the same kind of pre-filtration. So we use a system called a continuous deflection separation system. This is made by Contec, who's a partner of ours. And this is a relatively small system. These can be scaled all the way up to handle, literally hundreds of cubic feet per second of water pre-filtration. And usually off of really big rooftops or big parking areas, that's the way to pre-filter it. So the water has now been pre-filtered. We've captured it. It's got to go someplace. And generally it's going to go into a cistern of some sort. And as I said before, this is a very important discussion in the whole design process because of the cost of these different storage methodologies. And it can be something pretty simple like polyethylene tanks that might be in a basement. This is the center on Halstead in Chicago, where it's a Greywater system. So we only needed maybe 2,000 or 3,000 gallons total of storage. So that can fit in the actual storage area of the building at a relatively low cost. But more often than not, particularly with rainwater systems, we're talking about storage in the 10,000, 20, 30, 40, 50,000 gallon range. And in most cases, that's putting us below grade with some methodology. And that can be through fiberglass tanks, which are a very well-known entity by engineers. They love these things. They tend to be relatively inefficient because of the size of hole you need. They need a big crane to install them. They're very expensive. Same with concrete bolts, but these are both very acceptable methods. There's a chamber system like this that can be used on parking lots to capture vast amounts of water and then do some pre-filtration and use for application. If we're doing above-ground tanks, usually for irrigation in areas where we get cold winters, this is a Madison Fire. This is Madison Fire Station here. This is Skokie Police Station here, where the nice thing about these cisterns is that they are iconic. They basically show the public that this building is doing some kind of harvesting. They raise the interest level of the public about what's going on. So that's kind of a nice thing. They vary in size from 6-foot diameter to 72 feet and can be very, very large if we need them to be. And they can also be attractive from an architectural standpoint. These are some CoreGal tanks that were used in some creative ways in different kinds of buildings. So architects tend to like these things. Like I said, though, where we get sub-freezing temperatures in the winter, they're not really good for systems for toilet flushing. We have to have the water year-round. So generally in Illinois, these are emptied during the winter months, and then they're used during the summer for irrigation primarily. Another methodology that we are very high on and have been using in more and more projects is this rain tank system. These take recycled polypropylene and they make a plate structure like this. They come flat on pallets. They're assembled into these modular boxes. Just takes rubber mallet and hourly labor to put them together. They take about 10 minutes to make a quad like this. And the nice thing about these systems is, first of all, they're infinitely scalable from a very small cistern, 10,000 gallons, up to very large, 500,000 gallons or more. They can be in any shape. They can be, this is a 3-tank, there's a 4-tank. They can be 1 tank high or 5 tanks high, and an L or a square or a T. So they're very, very flexible. They're also lower cost than fiberglass or concrete. In addition to that, the way these things are put into the ground, we dig a hole. You'll see it with the case study in a minute. We dig a hole. We line the hole with an impermeable liner. So we've got basically a big swimming pool underground. Put a sand layer down. We wrap the tank in a filter medium, and then we compact sand on the sides, on the top, and below it. So what we have now is a system that is interactive with the soil around it, with the soil layer, sand layer around it. And we have basically passive water quality management. So through natural capillary action, thermal action, and just the water coming in and out of the cistern, it forces the water circulating through the sand layer up. We get a biofilm that forms on the tank matrix. We get some microbial action in the sand layer itself. And so what we have found that unlike a fiberglass tank, where if the water sits in a fiberglass tank for 2 or 3 months, it goes anaerobic, get off colors, off aromas, etc. The water that's in this system, just left to its natural state, will actually improve over time. It stays oxygenated. The water quality will clarify even more when it's in the cistern. So we have a passive control. We don't have to worry about sanitizing all the water in this system or circulating constantly. It's done naturally. So lower cost, highly flexible, and actually improves the water quality of water storage. So an excellent source of water storage. All right, so we've got the water stored now. It's pre-cleaned. We've got a big cistern full of it. Now we want to do the processing. And we talked before about the local communities, the concern about the water. They want to make sure the water is clean, the water is safe for public. So the processing stage is going to do a final filtration. We want to make sure the water is clear. It's not going to harm the valves in the toilet fixtures. It's not going to clog the sprinkler heads in the irrigation system. So depending upon the water source and the water use, we're designing a different kind of processing step. So here is just the relatively complicated Greywater skid, where we're collecting water from effluent sumps. We're going through a chlorination, dual filtration stage into a holding tank. We're monitoring chlorine levels and then pumping out. This is just a rainwater system where it's very simple 2-stage filtration through UV and then being pumped right out of there. So once again, we're matching the amount of processing to the location, to the water source, to the water use. Now, I've talked a little bit about the sanitation of the water, and sometimes the question comes about whether you got relatively clean rainwater, how unsafe really is it going to be? I mean, how much contaminants are there in there? Do you really need to go through a sanitation step? And our answer really is yes. In a public situation where we're exposing the public to this water, where we can have rodent feces, we can have bird feces, we can have other kinds of bacteria in that water, even off a clean rooftop, relatively clean rooftop, is that we do want to go through a sanitation step. And that really says we want to kill any microbial action that's there, any pathogens that are in the water, which does stabilize the water. So certainly in the case of Greywater, we don't have any more microbiological activity going on and creating black water out of that water. But even in rainwater, now we have the water safe. So there are many methodologies for sanitizing water in a system like this: UV, chlorine, chlorine dioxide, ozone, and others. The 2 methodologies which the industry is using now that have become standards would be first UV, ultraviolet sterilization. I would suspect many of you are familiar with this technology. Exposing any kind of cells to UV light destroys the DNA, which prevents it from reproducing. And the nice thing about UV is that it is a chemical-free methodology for cleaning the water, which means you don't have to worry about, in a green system, we're not adding chemicals to the environment. That's good. It's also very low maintenance. So these bulbs last about 10,000 hours, which means that a typical UV system may not need a bulb replacement for 2, 3, 4, 5 years, which means very low maintenance as well. So that's all good. The downside is that UV does not work well where the water is turbid. So if we have gray water that's got soaps clogging, it's really not a good methodology there. And the other thing too is that with UV sterilization, once it has left this UV process sterile, it is now eligible for being recontaminated downstream. So as it goes to the piping downstream, the toilets downstream, there's no residual killing value of UV. So we run the risk of it becoming recontaminated again. And that, from a public health standpoint, is a concern. So the other methodology we're using is chlorine, adding chlorine, which it's standard municipality. Here's a liquid chlorine system. Here's a dry hypochlorite system. And now chlorine is adding a chemical. We can manage the chlorine level, though, and keep the chlorine level about down to what municipal water would be, so it's not highly chlorinated. And the nice thing about chlorine is that it does have residual killing value. So we monitor residual levels. We keep them at about 0.5 part per million. And now as that water leaves our system and goes downstream, that chlorine continues to protect the water quality downstream. So we're not worried about the water becoming recontaminated again. The other thing, too, is that with UV, it's one of these, trust me, the water's safe. I've run it through a UV sanitizer. It should be safe. Trust me. The only way to know with UV whether the water really is safe and free of pathogens is to send it to an independent testing lab and have it tested. Whereas with a chlorine system, since we can monitor residual chlorine, we can basically certify the water is safe. As long as we're picking up residual chlorine levels, we know that the water has been treated effectively. And if we're not picking up that residual level, we can bypass it. We can send an alarm to the control system, to the building automation system, and say, hey, we're not picking up residual chlorine level. There's a problem. Usually it's because someone forgot to add chlorine to the hopper or something else. But the point is that if we cannot resolve that chlorine situation, we can automatically switch back to municipal water. So it gives us a backup safety step, basically, which we can't do with UV because we just don't know for sure that the water is safe or unsafe. Any questions? Okay. I'm going to move on then to pressurization. As we said before, I've lost municipal pressure for my water system now, so I have to find a way to get that pressure back so I can flush toilets, so I can irrigate the landscaping, etc. So in this case, there are many, many options for pressurization. Usually where we have a critical situation like toilet flushing, we put in duplex pumps so that if one pump fails, the other pump can take over, or the two pumps can work together in a high-demand situation. This is a relatively low-volume system here on one of our skids, up to a freestanding skid for a high capacity. This is the Panduit World Headquarters in Tinley Park, where we're flushing toilets in a very large building. Well, you'll see systems, too, where we're pumping out of a well, basically a wet well below grade. And the pumps, in this case, are using well pumps, which can be high capacity, low maintenance, etc. So we're just trying to decide what really is best for each building, depending upon its sources and uses. The last step would be the control system, and this is really the heart of the system overall. We have a lot of things going on where we've got filters and filter pressure. We've got pumps and variable speed drives in the pumps, which are revving up or revving down based on the pressure demands. We have cistern levels. We have to make a decision about whether we're on harvested water, municipal water, and whether we want to make up with that. We have valves that are being automatically turned back and forth. And then also we have data collection, reporting. So this system is meant to do all that. We do at Wahaso. We actually design and build these systems, and each system has screens that are customized to that location. So the building maintenance staff can see what's going on in the process. If there's an alarm, you can see visually where that problem is. And then also we have the ability to send this data from our control panel to an intranet so that data can be viewed from other parts of the building, or even to like a cell phone application. We want to do that as well. So that's valuable. They tie to the building automation system, so we can send system status and alarms to the building automation system so that you don't have to go down to the control room to see what's happening with it. And then there's also educational opportunities that I mentioned before, that many of our systems are for LEED certified buildings, or they're for educational buildings, libraries or schools, in which case there's a lot of interest in the system. They want to be able to explain what it does and how it does it. We want to be able to report on how much harvested water we've collected, how many rain events we've had, how much water we save for the building overall, what the trend is for the amount of water in our cistern, et cetera. And so this same system can monitor and data log all that and report that back through a consumer interface to be able to explain how that works. So all that comes together. Those are all the major components of a system, and they come together in basically a system like this. In a typical design, we have this is our CDS unit that's filtering the water off the rooftop. It's going into, in this case, a below-grade cistern, an Atlantis cistern. There's a transfer pump in the cistern, which is pumping water up to a day tank in the utility room. Here we're filtering the water into the day tank. We're adding chlorine into that water and monitoring residual levels of chlorine to 0.5 part per million. And then we're pressurizing out of that day tank up to the toilets in the building. Those are all your components. In a sustainable irrigation system, that can all be packaged together in a very small system that's not necessarily in the building. This is one of our outdoor enclosure skids. So you can see this is, we talked about before, a UV system with a couple of pre-filters and our controls all in this box. We put the pumping pressure below grade. So we have our cistern here. Water drains into this wet well. We pump from there. We can also monitor cistern levels from here, and we can do municipal makeup into here as well. So all that's happening below grade, out of sight, out of mind, and then we minimize the footprint above grade for that. So once again, how the system's designed depends on the building use, sources, and uses. If you look at the design build side of this, we're into 3D drawings now, so we can very accurately render what a system will look like before it's built. And then when it's built, it can be virtually identical to that, which gives us the flexibility of actually looking at options for how the system's laid out or how it'll fit in a room before we ever build it, which obviously makes a lot of sense. An example of some of the prefabrication that we do on skids, give you a sense of what these things look like. This will all be the operating. This is the system where we've got, here's our day tank, here's our chlorination system, here's the pumps here, pressure tank here, duplex pumps here, day tank. Here's you can't quite, I'll show you a better example later where we do the makeup in this, but then you see that the different sizes and shapes depending upon the kind of system we're building. All right? So that's kind of an overview of the systems. That gives you kind of a sense of what tools we're doing, what the priorities are, what the steps are. I'm going to take you through a couple of case studies here with the time we have left. I want to check if there's any questions I can answer. Yes? Well, certainly rainwater, no. Rainwater, condensate, I might be more concerned about greywater, where you realize there might be some contaminant soaps and things that we can't filter out, those dissolved solids. That would really depend on the situation. But we've used, usually what we're doing, almost every case, we're irrigating landscaping as opposed to food crops. So we might even have a situation where we want to separate perhaps the rainwater supply from the greywater in that case, so we're using the purer rainwater for the irrigation of food crops.
Residential areas, if you pick up any trace contaminants, or if you look at that,
it would depend on the material. I mean, there could be a situation, maybe a new roof where we're getting some, maybe on an asphalt shingle roof, there might be some concerns about that, particularly for a food crop, and that would, I don't know, we haven't done enough research to know whether over time if that's diminished to the point where it would be safe or not. Yes?
I agree with you that every design should be designed specifically for that. But is there any way you can ballpark the size of the system?
The size and cost. Well, yeah. I mean, what we'd say that what we see generally is these systems cost, depending upon the type, somewhere between $50,000 and $100,000 would be most of the systems. That would not include the installation of it. Would include, all of our components for that. The big cost factor is almost always the storage. So in areas where we get rainfall that's very seasonal, like in the Southwest, it takes a very large cistern to get us through that dry season and to try to capture as much water as we can. But that'll be the single most significant cost variation would be how much storage. And that really does depend. It can be a relatively small, where you get a lot of rainfall for a small use, could be 5,000, 10,000 gallons, or in a big commercial system, 30, 40, 50, 100,000 gallons. And that would, the system cost would scale proportionally. That answer your question? Most of the systems that we do for a commercial type building, storage is in about the 20, 30,000 gallon storage size, and the system cost before installation will be somewhere close to $100,000.
And if you have any specific, I'll show you case studies too. We'll talk about these costs as well. Yes, back here.
And just a comment, I want to ask you this, the building had built 3 housing houses, one lot, and collecting water in the swimming pool. So and the swimming pool was used as a dual purpose for swimming as well as providing irrigation and landscaping and so on.
So water level of the swimming pool sometimes
Real low, and sometimes it was real high. That would be the only downside of that, I would think. Yes. But it would be a problem if you thought today you were going to go swimming and there was only 2 feet of water in there. Yes.
You know, the primary filtration, you know, you use the soil, what kind of water, what kind of wastewater for this, you put the soil, for filtration? This is for green water or just like some building water? What kind of...
This is what I was demonstrating before. The primary filtration, you're asking, what would that be used for? What kind of water source? Or really, even off a rooftop, we put it through a pre-filter. So even rooftop rainwater would be going through that. Greywater would be very different. So that would be primarily for rainwater or stormwater. We'd run it through that type of pre-filter you saw there.
For the water from the building, like a toilet or...
No, we would do that. We would not do black water.
Black water, so no heavily contaminated water. So we would not try to treat either toilet water or like kitchen sink water that's more heavily loaded. We even try to avoid using washing machine, the first wash of water of that, just because it's just more difficult to clean, and there's generally other sources that are better than that for most properties. So but gray water would go through a different kind of filtration than we saw there. Well, we have a few minutes for a couple case studies quickly. Okay, let's talk about a couple of different projects we did. You'll see kind of a wide range of what we've done. The first is Fields Volvo in Northbrook, Illinois. Dan Field wanted to have the world's greenest Volvo dealership. And you can see here, this is the building as it was completed about a year ago with its wind turbines and its solar panels, and two of our tanks here showing up. And so he wanted it is all about showing his customers he was green. So when we told him the system was going to be about $100,000 and it would take him 25 years to ever pay that back in water savings, he didn't care about the water savings. It was about the PR. It was about the image of his building overall. So in this case, we went in and saw an opportunity to collect rooftop rainwater for 2 purposes, for both irrigation and for toilet flushing. So we have 2 storage tanks. We needed about 15,000 gallons of total storage for the system, and that we put 10,000 gallons below the surface with an Atlantis rain tank, and those 2 steel tanks above ground. And once again, the steel tanks were to show that he wanted to be able to demonstrate to his public that he was doing rainwater harvesting. We use chlorine for the sanitizer, and we save about 250,000 gallons of water a year. So for one of our systems, this is kind of on the low end because it was a relatively small building with a relatively low water demand, but still making a significant difference overall. You can see month to month the supply and demand. The demand is red. So here's our toilet flushing, which is pretty stable month to month. And then in the summertime, when we start irrigating, our demand goes up. And the rainfall we have in Chicago tends to kind of follow the seasonality. So we've got plenty of supply month in and month out so that we can virtually do all the toilet flushing and irrigation with this system, and virtually no municipal makeup required. So we start out with the schematic showing how it works. Here are 2 CoreGal tanks above grade. Here's our pre-filter going into the big 10,000 gallon cistern below grade. And then from there we pump up to a day tank. We're adding chlorine to that water to sanitize it. We're monitoring chlorine levels. And then we're pumping out the duplex pump system back out to the toilets. And we help out with kind of graphic illustrations like this of how the tanks will look and how they'll be laid out on the property. We provide the skid layouts like this too, so that the building owner, the engineers can see how much space they need for the system and can include this in their building design. So I'm going to show you how one of these Atlantis tanks goes in. It is kind of interesting to see. So this is that polypropylene structure we talked about before that's built on site. We start with a big hole. Dig a hole. These guys are putting a sand layer here to protect the bottom of the cistern from any pokes from sharp stones. They now come out and they line the cistern with this big rubber liner. So the liner comes shipped in one piece. Takes a bunch of guys to unfold it and lay it out there. But this creates the containment of the water in the cistern itself. And now we start putting another layer of sand below the tank. So this is just a flat sand layer. It's compacted down. Gives us a very firm surface for the tank. Also provides some of the filtration layer for the tank overall. And now we've got the geotextile that's going to wrap the tank itself being laid out. Here's the tank going in. So in this case, these guys built the tanks in the building that was being built. They assembled them there. You can see they can be carried by a guy on his shoulder and lowered in the tank manually. So we don't need any big cranes to install this. Just a few guys laying them out. You square them up. Here is where our transfer pump will be located. Here's where our level sensor will be located. Now the whole tank then is going to get wrapped with this fiber material. This is a geotextile fabric, which will keep the sand out of our void, if you would, but also allow water to pass in and out of that void into the sand layer. Now we're compacting sand all around it. So the sand around it provides a way of stabilizing the tanks, make sure it's very solid. And with 3 feet of cover above this tank, in the standard configuration, this tank can take an HS-20 load, which means you can put a parking lot above that tank. We can add a 5th plate. You can put a HS-25 load on top. You can put a fire truck on top of it. So it's very structurally sound and been successfully used in these kind of situations worldwide for about 20 years. There it is, all covered up. And we're assembling the CoreGal tanks here. And this is a permeable pavers. Because there is no top to the tank, there's just a sand layer and a filter medium, you can actually infiltrate from the top down. So these can go underneath a vegetated swale. They can go underneath a play field, for example, and the water can be dumped into that vegetated swale and then drained into the top of the tank that way for capture passively without having to pump it in. Here's our skid installed in the mechanical room. Here's the day tank, the chlorinator, duplex pumps. Here's the air gap. So remember I said that one of the concerns municipalities had that in a backflow situation we would be drawing this non-potable, unsafe water into the potable system. And so Chicago and other states require that we have an absolute gap between the municipal makeup supply here and our non-potable supply. And that's done here with this funnel. And we turn that water on when our cistern's empty and we have a demand for water in the building. This system minimizes the amount of maintenance by having a secondary. This is our filter that does the final filtration. It's a self-flushing filter, so it requires no maintenance. It automatically back-flushes itself, which saves on the maintenance time and effort. And then here's our control panel monitoring the system and managing the overall system. That's the Fields Volvo. Let's go to Hollywood, across the country to the Hotel Bel Airs in the Hollywood area. This is the Hotel of the Stars, very upscale suites of buildings in the Bel Air area of Hollywood. As you can see, we have very lush landscaping around this building, and we're in a very arid part of the country with very little rainfall. So they wanted to do a whole rework and add a lot more villas to this system, and the city of LA said you cannot use municipal water for irrigation. And so in this case, they said we got people taking showers with 20 gallons a minute showers. They had a lot of gray water, right? And they do. Let's use that gray water then for irrigation. So that's what we've done. We've created a gray water irrigation system. It saves about 240,000 gallons per month, which is 10 times what the Fields Volvo project did, or about 3 million gallons of water annually. It was commissioned just a month or two ago, so it's still a brand new system for us. Now, looking at supply and demand here, we're not talking about how often it rains, how big the rooftop is. Instead, we're talking about how many people are taking showers every day. That's our supply. And the variable factor here is not how many showers we have, but what our occupancy level is. And so as the hotel occupancy goes up, so does our supply goes up. So this was a way just to kind of model for them how much supply we'd have, with low occupancy versus high, versus how much water were needed for irrigation. They figured it was about 6,000 gallon per cycle of irrigation. You can see then the water savings we have month to month, or annual, actually year to year, depending upon what our average occupancy rate is for the hotel. Here's our schematic showing how the system works. In this case, we're capturing water into a settling tank, the gray water. So we're separating the gray water, trying to get the floatables out of there and the solids out of the gray water, filtering it through a system, and then storing that in a 5,000 gallon clean tank water below, so it's staged and ready to go for irrigating the landscaping. Some of the 3D modeling we did, here's the filtration skid here. And for Greywater, we start with a bag filter. This is like a 100 micron bag filter. And that's really to get out all the big particulates, the hair and other things that can be problematic in our main filtration system. So this is a high capacity bag filter, so it's only probably replaced every couple of months at most. And then most of the work's done by a multimedia filter. So the multimedia filter is able to separate all the solids out down to about 5 microns. So it's getting the water very clear out of that gray water. At the same time we're adding filtration, we're also injecting liquid chlorine. So we try to protect our filter mediums with a liquid chlorine solution being injected before it goes in. And then we also monitor chlorine levels in our storage tank to make sure we're maintaining at least a half a part per million of chlorine in our readied water for usage. There's our settling tank design. And then because we had 3D modeling, we were actually able to figure out how to fit all this equipment into a very small room. And so the engineer gave us the room dimensions, and we played back and forth the 3D model to try to, before we ever sent equipment there or built it, to see how it would fit in the room, which was important in this case. And here's the equipment when it was manufactured, the settling tank. Here's our dual-stage filtration, chlorination system, and our control system. So that's a Greywater system. Room for one more? Questions? Okay. So any questions about that? You've seen some Greywater, rainwater, and kind of a good sense of how we do these systems? Yes?
What's the lifespan of that lead?
Which component? I mean, probably the shortest lifespan would be the pumps in any system like this, not unlike any other pumps in a building. So they're expected to last on the short end 5 or 6 years, 10, 12 years beyond that. But really everything else is going to have a much longer life cycle, from our experience. That in the below grade system like that pool liner is rated for UV exposure for 20, 25 years. And this is below grade with no air or UV exposure. So the current guess is you've got 30, 40 years, and no one really knows how long this will last. I don't know. Talk to me in 30 years. I don't know. I would guess, yeah, you'd probably do that. You'd probably just have to dig it up. Now, the polypropylene structure would last forever, so there's no reason why you couldn't remove those tanks, unassemble them again, reline the excavation, and refill it back. I mean, that's happened in the past. I know they've had to redo a tank. Any other questions? Yes.
What was the payback?
Which one?
Bel Air.
Hotel Bel Air? Well, if we go back here, look at the savings we have per year, $14,000, $15,000 per year at current water rates. And I always say that because water rates in LA are rising quickly. The total system cost installed was probably in the $150,000 range. So at today's water rates, about 10 years. And I think that as water rates go, that ROI will improve dramatically in the next 3 to 5 years. Any other questions? Yes. The liquid chlorine, we've only done a couple of systems like that in big commercial buildings where they already have scheduled maintenance for that. Someone bring in a 50-gallon drum. But, our systems don't use that much chlorine. And so the little hypochlorite tablets, like a swimming pool, that's our primary methodology for chlorine. I mean, that little hopper lasts, a month or two at a time. And so those are easily replaced without any kind of hazmat kind of material handling requirements of gloves and face masks and stuff. So that's really the preferred methodology we've seen.
Well, thank you very much, John.
Well, you're welcome. You had a great audience. Thank you.